Hello all, we are here for our last section in chapter 14, which is 14.4 lengths of curves. And so we're going to be finding the lengths of curves in 2 and 3 dimensions. So just a quick reminder of something that we know from Math 252. So you have a formula for an arc length, or the length of a curve in 252 that we find, by taking a curve like the one we have drawn here and taking and chopping it up into little pieces like we do with everything in 252 and figuring out the lengths of those straight lines and then adding each of those up, and then that leads us to our integral. And where this starts is that we're finding the individual lengths, so we could call it length sub I, and it's the square root of that delta x squared plus delta y squared. And then we have, oops, and maybe we need to put a sub I on there for our little subinterval that we have. So it's, taking each of those little lengths, adding those up and making those lengths smaller and smaller so that that summation converges to an integral for us. So this is very, very similar to what we're going to do with our vector valued functions. It's pretty much exactly the same. So here's what we're looking at in 2 dimensions. So we've got a parameterized curve. So again, that's just a vectored value function. That's what that's talking about. And we're talking about in 2 dimensions. So for example, we've got, our curve doing this and it's got direction to it. So that's what we're talking about here. And with this, f prime and g prime are continuous on our interval a to b, and then our arc length of this curve is going to be the integral from a to b of the square root of f prime of x, or f prime of t, excuse me, squared plus g prime of t squared. So, sort of thinking about where this comes from on this picture here, if we take 2 points on this, again, we can approximate that curve with this straight line here, that um, straight thing. And then we can make a little right triangle. And our length here, this is our change in x. And this length here is our change in y. And we're parameterized. So when we are thinking about, you know, that this length here by the Pythagorean theorem, so that length, and again, we can call it length sub I, is going to be the square root of that delta xi squared plus delta yi squared. Now, because this is parameterized, instead of looking at it as the change in x and the change in y, because x is in terms of this function f of x and g is, or y is in function, y is in terms of our function g of t, boy, we can replace that delta x with delta f squared, and this guy here with delta g squared. So again, we're changing from being in terms of x and y into being in terms of our functions with respect to t, our parameterized way of looking at x and y in terms of vectors versus just being, regular x and y. So basically what we can do with this, because of the mean value theorem that you learned way back in 251, that said if we've got that secant line that ends at A and B, there's somewhere in there where you've got a tangent line that's got the same slope as your secant line. So you can essentially change that secant line into a tangent line. I am literally doing some hand waving while I'm saying this. So we're doing a little bit of calculus hand waving. And this leads us to being able to say, okay, this is the derivative at t, the derivative of f at t squared plus the derivative at g of g at t squared. And again, these all could have a little sub I or a little star there to talk about it as that point in that interval. And actually, instead of being on the f and the g, they would likely be on the t there. But again, what we can do is take all of these little straight lengths And we can make that interval, make the intervals smaller and smaller, smaller and smaller, and we can add them up. And then that leads us to our summation, which we can change into our integral. So we won't go through all of that. That's not the most important thing. The most important thing is that we know about this, formula, how it works, that it's the components, their derivatives squared, and then square rooted. Hopefully this looks familiar here. We'll talk about it here in a second. That when we look at this in terms of a three-dimensional arc or curve, things don't change very much. This is our more, so the last page was kind of my sort of ref definition of what this is. This is the more specific definition from our textbook. And so the things that have to be true is that f prime, g prime, and h prime need to be continuous. That's our mean value theorem part of that. And then the curve that we have is traversed once. Okay, so what that traversed once is, that's kind of a weird sentence. So traversed once looks like that. It's we say, well, how is that traversed once? How that is traversed once is, let me show you something that is not traversed once. That's sometimes a better way to do it. Something that's got, say, a loop in it, where we traverse that interval, but then we loop back around and traverse it again. That is not traversed once. So we're trying to avoid any curves that do this kind of thing, where they loop back around on themselves. And most of our curves that we deal with are, these kinds of guys, that they go straight, or it is just a piece of wire that's not like curved back in on itself and doesn't cross itself. So this is, that where that curve is crossing itself. So we don't have that. Um, and that's not something we have to look for a lot. We don't end up with a lot of problems where you have to figure out whether or not it's crossing itself. The curves that we're going to give you are going to be traversed only once, from A to B. And then our arc length of that curve is, again, the derivative of each of those components squared. And it looks like I did leave out one squared here. I'll fix this when I look at the notes there. That should be h prime of t squared. And if you think about this, this is the derivative of our position function. If we think about this as position, the derivative is that velocity function, and this is the magnitude of the velocity. So this is actually the integral of the speed. Sorry about that big old ding if you heard that. Apparently my notifications are turned on my computer. Very loud. So that was our note, that this arc length is going to be the integral of the speed, or you could write it as that it's the derivative of our position function. Let me get those as vector valued functions. And so that was our little extra note about that we want to pay attention to. That's kind of interesting that we get the integral of our speed. All right, let's do a quick example of this. The nice thing about these problems is that they're all fairly straightforward, and the square roots tend to nicely simplify themselves. So really be watching for things that factor, common factors, Pythagorean theorems where you can replace sine squares and cosine squares with 1. So I kind of tend to do these things in pieces. Um, so I start with finding that velocity function, or again, it's that first derivative. So we're going to get 12 for our first component. We're going to get 8 times 3 halves, and then x to the 1 half, and then 3 times 2t. I guess I'm being extra showy of my work here. There we go. So we should get 12 for the x component, 12 times the square root of t for the second component, and then 6t for our third component. And then we can put them all together right away, but something, again, also I like to do is do some of the simplification not inside of that integral. You can do it all as one big problem. That's kind of up to you. I'm kind of one of these people that I don't like, having to write my integral symbol every time and put my dx every time. So I'll often kind of do some work off to the side, say, okay, that's going to give me 144. This is going to give me 144 times t, because the square root squared is just going to be t. And then this is going to give me 36t squared. So now this is actually what's going to go inside of our square root. So 144 plus 144t. And you know what? Maybe I don't like it written in that order, so we can rearrange that. Let's write 36t squared plus 144t plus 144 dt. And so remember this interval that we give you, that's our limits of integration. So things that we want to look for with this is, are there any common factors? So one of the first things that I checked is I divided 144 by 36 to see if we had a common factor of 36. And what was wonderful is that we absolutely do. So we can factor out that 36 and you end up with t squared plus 4t plus 4. And then this quadratic that we're left with here, that is a perfect square. So like I was saying, watch for common factors, watch for factoring, because things should be pretty nice on these, and it should end up that either you end up with a square root that you can take the integral of, or you're going to end up with something you can take the square root of, and that square root will be gone. So that's what we end up with here, because the square root of 36 is 6, and then the square root of t plus 2 squared is t plus 2. So this is really nice. It turns it into a super simple integral that we can take. And we are going to get 3t squared plus 12t, and we're looking at it from 0 to 1. So if we use our fundamental theorem of calculus, we get 3 plus 12 minus 0, which is going to be 15. So the length of our curve is 15.